In this video, we're going to discuss the calculus of vector-valued functions. So, namely, how we can take the derivative and the integral of a vector-valued function. And along the way, we'll also discuss this notion of a unit tangent vector. Okay, but to start with, the derivative of a vector-valued function. So, well, you have this definition, which looks really similar to the Calc 1 definition of a derivative, right? It's the limit of the difference quotient. You at a specific time t, you then have a time step delta t, then you subtract the two function evaluations and then divide by. So in Calc 1, the delta t would be normally expressed as like h, and you let h go to 0, so it's like a plus h minus f of a over h. So we have the same type of definition for the derivative. But in practice, when you're trying to compute an actual derivative, what you can use is the property that the derivative of a vector-valued function is the derivative of each of the component functions, which is written here. So in practice, that is what we will use instead of this limit definition. Okay, and you can see an example. So here we have the vector value function r of t defined as such. And then to compute its derivative, you just take the derivative of each of the component functions. So this exponential, there's a small chain rule involved that will pop the negative out. And so you get minus e to the minus t. Here we have another chain rule happening. So you'd have a cosine of 3t times 3, which is right there. And then with this, well, it's a very common pattern. The derivative of a square root, when you take the derivative of square root, it's 1 over 2 square root of x. You might be more comfortable with thinking of the square root as a fractional power, in which case, taking the derivative, you would get 1/2 x to the negative 1/2 using the power rule, and then re-expressing this as a radical, you'd get a square root in the denominator, so you get this. So the shortcut way is just to kind of recognize this pattern, right? Derivative of square root makes this pushes the square root into the denominator, introduces the 2 into the denominator, and so you have the cancellation shown there. Right. Now some properties of the derivative. So these are nice to know, but I don't think that you see these being used in the homework. But it's just good things to know. So first of all, the derivative for vector-valued functions is linear, just like how the derivative is linear in ordinary Calc 1. So scalars you can pull out of the derivative, and you can distribute the derivative over terms. Right? So pluses and minuses. Next, the derivative satisfies 3 different product rules, because in the setting of Calc 3, we actually have 3 different types of products. We can do a scalar product, a scalar function multiplied by a vector function, a dot product of 2 vector functions, and a cross product of 2 vector functions. Okay, so you can think of it as, like, if we actually had a specific value t, like t equals 2, for example, then f of t would just be a number, u of t would be a vector. So you'd be multiplying a number by a vector here. And so you'd have a vector function here, you'd be taking a derivative. So this makes sense. And then in these two, you'd have a vector dot a vector, and a vector dot and a vector cross a vector. So you end up having a resulting vector function. And so the time derivative also makes sense for these expressions as well. And yeah, you can see that these satisfy the typical product rule that you're used to. So in the ordinary Calc 1, it would be this is equal to f prime g plus f g prime. So here we just have it, but dealing with vector functions. There is one important thing to notice. The order matters for this one. Order matters here. So since the cross product is anti-commutative, so we cannot swap these two around. We cannot say u prime cross r prime, because that will introduce a negative into the expression. So it actually is important that we follow this pattern specifically. The f and g stay in the same order, and then the primes are on different guys. So we have the same order, but the primes are different guys in this product rule. And the last property is this chain rule. So just like in Calc 1, it follows very similarly. So if we take the derivative, then we get f prime of g of t times g prime of t. That's the chain rule from Calc 1, and you can see that we have the same type of expression here. So r prime, and then we plug in the inner function, multiply it by the outer function. Let's think about what type of product this is. So this is a scalar function, this is a vector function. So it's a scalar dot a vector. So this is just scalar multiplication. Okay, so not too fancy. And if my typesetting was a bit more clear, this would actually not be a bold dot, but a small dot. So these are supposed to be slightly larger than this. Maybe whatever. Okay, next topic is this notion of a tangent vector. So a tangent vector is basically what you would think it is. It's a vector that is going to point in the direction of change along a path. So it's going to lie tangent to the path, the curve. So if you have a curve C that is defined by a vector function R, then a tangent vector is tangent at a specific point t naught if when you line it up. So in this picture, for example, you'd have that this vector in green would be r of t naught. And so when you line it up head to tail like so, the derivative, or well, the tangent vector, we're not, right now I'm not specifying that it's supposed to be, it's any tangent vector. So any tangent vector t, if you line it up head to tail, it is going to be perpendicular, I want to say. Maybe not necessarily, although I think it might. That's a calculation that I'd have to check. But it will behave in the way you'd expect a tangent vector to behave. So it'll be tangent to the curve. Yeah. So this will be your vector v r of t. And specifically, we want to call out the principal unit tangent vector. So this is a specific tangent vector. We could have a whole range of them. You could scale this guy up or flip the direction of it. And these would all be technically tangent vectors. But the one that we want in particular should be of unit length and should be in the direction of travel. So along this curve that is in pink, you can imagine the direction of travel is in this way. So that specifies which direction. Otherwise, you would have a vector pointed this way of unit length. But we kind of want the tangent vector to tell us what is like the actual change that is taking place as you go from one time step to another, which you can kind of see from this picture. And so actually by considering these pictures, you can notice that the vector in blue is the limit, right, of the difference quotient. As you change the separation of the time steps closer and closer, this subtraction, the resulting vector, ends up getting closer and closer to being a tangent vector. So that is why the derivative will compute for you a tangent vector. And then to get the principal unit tangent vector, you normalize. You divide by the magnitude of r prime. And so you have this expression denoting the principal unit tangent vector. Okay. And, well, we have a problem that asks us to compute the unit tangent vector for a given vector function. So here we have the vector valued function r of t is 3 cosine 4t I plus 3 sine 4tj plus 5tk. The fact that the t runs from 0 to 1, that doesn't really play a role here. So the process is that you are just trying to compute the formula. You're trying to compute r prime of t divided by the magnitude of r prime of t. So we start by computing r prime of t. which means that we take the derivative of each of the component functions. So that just involves a chain rule, right? So cosine of 4t, its derivative is negative sine of 4t times 4. And so you clean it up to get this. Derivative of sine of 4t is going to be 4 cosine 4t. So you get this, and then 5t is going to be 5. So that is the derivative. That is r prime of t. Next, you take the magnitude. So that's you square each of the components, you sum them together, and you take a square root. You're using distance formula. And so now you have to be a little bit more careful with the calculation because it's not numbers, it's functions, and we can do a simplification. So you should know the property that sine squared plus cosine squared is equal to 1. We use that property here. We have these two terms, which I can factor out 144, and we end up with sine squared plus cosine squared. And so that is just 1, which leaves you with 144. And the 25 sticks around. And then this is actually, when you add it together, 169, which is a square number. So you can take the square root really easily. You get 13. And so the unit tangent vector requires us to divide. We then divide through each of the component functions by 13, which then gives me this vector function. Okay. Now, integrals. So integrals behave the way you would expect. So just like derivatives, you can pass the integral through each of the component functions of your vector valued function. So yeah, you just integrate each of the component functions, whether you're talking about a definite integral or an indefinite integral. It works the same way. Though one thing to comment is that when we get this expression, in practice, we might have to tack on a constant, which is going to show up, right? So just like with ordinary integration, so I didn't write the constant here, but that's kind of because these integrals have constants in them. Yeah, so, but we would have a constant, and the constant actually would be a vector, right? So let's see an example. So in this problem, we're given an acceleration function, and we're given an initial velocity and an initial position. So the initial velocity and the initial position are vectors. Acceleration is a vector function. And to compute the velocity function and the displacement function, displacement, is that the right word? Well, position function, fine. Computing a position function and the velocity function, you have to take the integral, right? So just like in Calc 1, the derivative of velocity is acceleration, the derivative of position is velocity, and when we integrate both sides, we get the formula that we're working with. So to compute the velocity function, we have to take the integral of the acceleration function, which we do here. Pretty straightforward, I think. Yeah, just integral of sine and cosine. The only thing is that we have a constant to work with, and we have to solve for the constant. That's why we have this initial velocity vector. So when I take this velocity function that we found and I plug in t equals 0, I end up with this. Oh no, I end up with this term, and but my data given tells me that it's supposed to equal 3i plus 4j. Right? When I plug in 0, I get minus 2, 0 for j, and then I get a plus c. So we have to solve for c. Adding the 2i to the other side, we get 5i plus 4j as my constant vector. And so plugging this back into here, and then regrouping so that we have I and j, collecting the i's and j's, we get minus 2 cosine t plus 5 as my function in the x-coordinate, and minus 3 sine t plus 4 as my function in the y-coordinate. So we have this as the velocity function. Now, integrating the velocity function will give us the position function. So we integrate, which is not too difficult. And of course, we also have a plus c at the end. plugging 0 into the position function, our given data tells us it should equal 5i plus 6j, but when we compute it, we end up with 0i plus 3j, yeah, plus a constant. So solving for the constant, we minus the 3j over, we get 5i plus 3j as the constant. And then plugging this back into r of t that we calculated and regrouping, we get this final expression for the position function. And so that's everything we're asked to do. And that's all I've got for this topic.